Let's talk about the P operator and impedances. At the end of this set of slides, I expect that the student should be able to write the P impedance of an inductor and of a capacitor as well. Should be able to combine those impedances in series or in parallel. Should know the units for the impedance and determine the differential equation that one would need to solve to find any voltage or any current in a circuit. Observe that I emphasize we want to find the differential equation. This set of slides is not about solving the equation, it's only about finding, which is going to be critical in electric and electronic circuits. We begin with two names you remember from your physics and mathematics course. In second year, we wrote differential equations using mostly Leibniz notation. We would write something like this: 3 times the second time derivative of y. Y is a generic function of time, plus 5 times its first time derivative minus 8 times the function equals to 14. 3 coefficients, 3, 5, and negative 8, the coefficients of the differential equation, order 2, and a right-hand side term. But there was another notation we learned in second year too, or one introduced by the other father of calculus, Sir Isaac Newton. He used this elegant way of representing the same differential equation: 2 dots for the second time derivative and 1 dot for the first one. Again, we see the 3 coefficients of the differential equation and the right-hand side term. Today, we will bring in Oliver Heaviside, an English physicist of the 19th and 20th century that came up with this alternative notation. He says, instead of d over dt as a symbol, I will use only p, an operator, and instead of the second derivative, just p squared. And instead of writing the integral of some function dt, I will just write 1 over p. If we apply the P operator notation to the differential equation shown in Leibniz notation, we would write 3 times the second time derivative of y, sure, 3 times p squared y, plus 5 times the first derivative of y, that is plus 5py, minus 8y equals 14. Observe we still have the same 3 coefficients on the left-hand side and the right-hand side term 14. The order of the differential equation can be seen up here. P squared is a second order one, but we can do something else. We can factor out y like this. Don't be surprised, I have not solved it. I have only rewritten the same differential equation. Again, we see the coefficients 3, 5, negative 8, and the right-hand side term. I'm only emphasizing that one only unknown in the differential equation, y of t. We could do something else. We could move all of these parentheses dividing to the right-hand side and write the differential equation like that. It's no solution. This is the same differential equation written in a different form. We have the coefficients for each one of the terms of the differential equation on the right-hand side term. And the order of the differential equation appears as the maximum exponent for the polynomial in the denominator. Observe, this is only another way of writing the same differential equation, but one that will be extremely convenient to us electrical engineers when we find a differential equation in a circuit. To differentiate then, we just pre-multiply by p like this. The derivative of the derivative of y, that is just p of y, that is p squared y. And to integrate, we just divide by p. So the integral of the second derivative of y, that is just 1 over p, that multiplies p squared y, and that is py. That is the first derivative of y with respect to time. Now let's apply the P operator to two differential equations that are very close to us in electric and electronics technology. Those are this equation, V is L di dt, and I is C dV dt. The first one in words is the voltage in an inductor is L times the derivative of its current, and the current in a capacitor is C times the derivative of its voltage. Let's begin with the inductor. That is a current, that is a voltage, polarity, direction. Water falls from the sky. Current is flowing from high voltage to low voltage, so we can write that differential equation. V is L di dt. Writing that using the P operator instead of di dt, we write Pi. So we write V is LPI. Fine. Keep that in memory, and let's go on for the capacitor. In the capacitor, again, same polarity for the voltage and direction. For the current, it's the absorbing power convention, and we wrote that differential equation I C dV dt in the capacitor. We can solve for V, and it's 1 over C integral of I of t. And then we use the P operator notation. The integral of I is I over P, so V is 1 over C pi. Remember those. Remember this one, the very last one. Let's write all of them together. For resistors, however, V is Ri hasn't changed. That is still Ohm's law. For the three of them, for the inductor, V is LPI. For the capacitor, V is 1 over CPI. And for the resistor, V continues to be Ri. So if we define ZL, the impedance of the inductor, as LP, ZC, the impedance of a capacitor, as 1 over Cp, and ZR equals to R, we can write all of those three equations just as V is Z times I. Ohm's law all over again, just by the introduction of impedances in the P operator domain that way. Impedance of the inductor, LP. Impedance of the capacitor, 1 over Cp. Impedance of the resistor, its resistance R. Hold on a second, you say. We have defined impedances already before. Remember, with phasors, we said the impedance of an inductor is j omega L. The impedance of a capacitor is 1 over j omega C. You say, hey, wait, wasn't that negative j 1 over omega C? It's the same thing, remember? Negative j is 1 over j. So the impedance of a capacitor is 1 over j omega C, and the impedance of the resistor was R. But right now, we have redefined them as the impedance of an inductor is LP. In the P domain, the impedance of a capacitor is 1 over Cp, and the impedance of a resistor is R. But that is not all. Soon enough, in the near future, only in a couple of weeks, in the Laplace transform domain, we will redefine the impedances again. The impedance of an inductor will be Ls, the impedance of a capacitor will be 1 over Cs, and the impedance of the resistor will remain unchanged, R. So we have traveled from j omega to P, and in the future to S, to the complex variable S of the Laplace transform domain. We have reacquired the general Ohm's law. For any element with an impedance Z, we can write, agreeing that the current is flowing from high to lower voltage through it, as V is Z times I. That is Ohm's law. What are the units of that impedance? Well, observe the units for V are volts, the units for I are amps, so the units for Z have to be volts over amps, which is ohms. Or if you want to be a purist and you want to do all the simplifications of units, I invite you to do that, and you will find that actually LP is ohms, as in this case, or that 1 over Cp is also ohms. So ohms are the units for impedance in the P domain. Now, impedances in series or in parallel, or Y2 deltas or delta 2 Ys. Because impedances, the way we defined them a moment ago, follow Ohm's law. V is Z times I. And because we still have KVL and KCL, of course we can combine impedances in series and combine impedances in parallel the very same way we did with resistors, right? We can transform them from delta to Y's and Y to deltas, and we can even use M&A in the P operator domain, which we will be doing in a moment. Now, tutorial time. Let's find the equivalent impedances of those branches. A 2 ohm resistor in series with a huge, humongous 3 Henries inductor. Of course, I'm using those huge, ridiculously huge values for inductances and capacitances for the sake of computation on the screen. So I replace the values of the elements by their P impedances. 2 ohms continues to be 2 ohms, no change. And 3 Henries, well, the impedance of 3 Henries will be 3P, LP, remember? In series, they are just 2 plus 3P, that is the impedance of that branch. Let's do one that is a bit more interesting. 2 becomes a 2, no change. 3 Henries is a 3P ohm impedance, and we put them in parallel is the inverse of 1 over 2 plus 1 over 3p. We do some simplification with a calculator, and we get that the impedance of that branch is 6 times p divided by 3p plus 2. Let's do one more. 2 ohms resistor in series with a 5 farads capacitor. Replace those by their p impedances. A 2 is a 2, but 5f is 1 over 5p. Now we combine them in series like that, evaluating the calculator to get a simplified version of the impedance. One last 2 ohm resistor in parallel with a 5 farads capacitor. The 2 ohm resistor continues to be a 2 ohm resistor, but the 5 farads is 1 over 5p. Parallel is the inverse of the sum of the inverse of 2 plus the inverse of 1 over 5p. Evaluate, simplify, that's the impedance in the p domain of that branch. So remember, we can use simplifications, y to deltas, delta to y's. We can use M&A, loop analysis. We can find Thevenin equivalence using p operators. But if we have KCL, which we do, and we have KVL that we also have, and we have Ohm's law, of course we can replace elements by their Z, by their impedances, and use modified nodal analysis the way we have been all along. Let's do an exercise. Let's take this circuit. We have one DC source 12 volts, resistor 3 ohms, an inductor 2 Henries, a capacitor 1 over 5 farads, and another resistor 7 ohms on the far right. The first thing is to replace all the reactive elements by their P impedances. And they will be 2 Henries becomes 2P. 1 over 5 farads becomes 5 over P. And then what? And then we solve the circuit using M&A. You say, what are you going to find? Well, they should tell us what we want. We want to find a differential equation. For what? Let's say we want the differential equation for the voltage in that node 1. Reference node, node 1, branch currents, chosen like that. And then we write a KCL equation, right? Currents going in, 12 minus V1 divided by the impedance of the branch, 3 plus 2P. That is equal to currents leaving the node, that is V1 over 7 on the far right, and V1 over 5 over P. And we go and we solve for V1. And that will be the differential equation whose solution would give us V1 in the real world. But instead of using sort of hand substitution and all of that stuff, I will use the HP 50G or 49G to find V1. How? First thing is I make sure that I wrote in the KCL equation there already, but I want to make sure that the independent unknown of the calculator coincides with whatever name I gave to the variable V1 there. How do I do that? I go to Mode, I get that, and CAS, and in there at the very top I have the dialog box for the independent variable. I edit that with this button and I make sure that it's V1. At the same time, I like clearing all of these radio buttons, pneumatic, approx, complex, verbose, all of them. Clear them all. And then, okay, we are ready. We're ready for what? Symbolic solver, and then solve for x. You don't see the x there because there were too many letters, and the calculator cuts after 5. Solve, and you get that V1 is 420 divided by 14p squared plus 31p plus 50. But that is no solution. That is a differential equation with the coefficients 14, 31, and 50, and the right-hand side term of 420. We're solving for V1. That is a differential equation that we would write using Leibniz notation like this. Observe the coefficients of the left-hand side, 14, 31, and 50, and the right-hand side term for 20. The order of the differential equation is given by the highest exponent of the denominator in the heavy side representation of the differential equation, second order. That is the equation we would need to solve to find that voltage V1. And then what do we do then? Well, now that the differential equation whose solution is the voltage we want or the current we want, we just have to solve it. Well, that is not the goal of this set of slides. We will worry about that later. But let's say that in that same circuit, we are told after finding V1, no. What I want is not a differential equation for V1. What I want is a differential equation for the current in the source. Well, if I have V1 already expressed like that, I say the current in the source is just 12 volts minus V1 divided by 3 plus 2p, right? And I have V1 in the calculator, so substitute, simplify, and I get my equation. Yeah, how am I going to do that? I have on the calculator already V1 for 20 divided by a polynomial. I write 12, swap, subtract, and then divide by 3 plus 2p, divide. That has to be IS, right? Evaluate, and that is the differential equation for the current in this source. I have come up to this current in this cumbersome way. There is an easier way to find that because it forces us to find out, to deal with the P on the right-hand side. Check it out. I'm copying that over here. What does it mean? You say, well, what it means is that the differential equation that would give us the current in the source is second order. You see, the polynomial in the denominator is a second degree one. The coefficients of that equation are 14, 31, and 50, which, by the way, are the very same coefficients that the differential equation for the voltage had up here, 14, 31, and 50. What is that right-hand side? Because I can move the denominator over to the left-hand side like this, and the left-hand side makes sense. 14 times the second derivative of is plus 31 times the first derivative of is plus 50 times is equals 2. What is the deal? Let me write that using Leibniz notation, and everything will become clear. The left-hand side is crystal clear, but the right-hand side, 84 times ddt plus 60. ddt of what? There is no function of time. Well, in that case, we say we're applying ddt to the number 1, ddt of 1. But 1 is a constant, so ddt of 1 is 0. And that ends being this differential equation, whose solution will give us the current in this source. In reality, I would have solved that circuit completely differently. You see, I better show you. I would have rather just found what is the equivalent impedance seen by the source and divide 12 volts by that impedance. Let's do just that. I begin typing in the impedance 7 and the impedance 5 over P using the equation right. And then invert the first one, swap, invert, addition, and invert. That is the parallel impedance on the right. Now Add 3 in series, go back to the equation writer to write 2p. Add that in series too, simplify, and that is going to be the equivalent impedance seen by the 12-volt source. Now let me type 12, swap, divide, and simplify with the evaluation key, and that's going to be the same differential equation that we had before, painlessly. Well, that is all for now. Thank you very much, and I hope to see you again in the next movie.